We have solved quadratic equations using two different methods, and now we're going to move on and look at some applications. The main one that we're going to look at is motion under gravity. And to begin, I want you to watch this little YouTube clip of a sitcom that is near and dear to my heart. It is called The Big Bang Theory, and this is Season 1, Episode 1 if you're interested. But it's about two physicists and their adventures together, I'll say. So, enjoy.
Okay. Her apartment's on the 4th floor, but the elevator's broken, so you're gonna have to... Are you just gonna be done? Okay, cool, thanks. I guess we'll just bring it up ourselves.
I hardly think so.
Why not?
Well, we don't have a dolly, or lifting belts, or any measurable upper body strength.
We don't need strength. We're physicists. We are the intellectual descendants of Archimedes. Give me a fulcrum and a lever, and I can move the earth. It's just a matter... I don't have this. I don't have this. I do not have
Archimedes would be so proud.
this. Do you have any ideas?
Yes, but they all involve a green lantern and a power ring.
Easy.
Easy.
Okay. Now we've got an inclined plane. The force required to lift is reduced by the sine of the angle of the stairs, call it 30 degrees, so about half.
Exactly half.
Exactly it. Let's push. Okay. See, it's moving. This is easy. It's all in the math.
What's your formula for the corner?
What? Oh. Okay. Okay, yeah, no problem. Just come up here, help me pull and turn.
Ah, gravity, thou art a heartless bitch.
Well, so gravity really isn't that heartless. It's just a law of the universe. So, and it turns out that the mathematics of gravity isn't all that complicated. And so the only thing we have to use in our assumptions here as we work through problems related to gravity is that we're going to work with objects that are experiencing gravity under ideal conditions. So we don't have any other sources of friction, so we're ignoring air resistance and that sort of thing. And we also want to be sufficiently near the surface, so we're not like tossing things, or we're not dropping things from, say, 5 miles up. And then we also want to make sure that we have constant acceleration. And under these conditions, the formula that we're going to use looks a little different than what you're going to see in Hawks, but this is the formula that physicists use. D is equal to D naught plus V naught T, or you can say subscript 0 on each of those as well, plus 1/2 AT squared. Okay, so let's talk about what each of the things means. Okay, so D is final position, so where it ends up. D0 or D naught is called the initial position. V0 is called initial velocity or initial speed, depending on the context. T is time for sure, and then A is acceleration. And then just make sure to pay attention to units. So if we're working in the metric system, distance is generally going to be in meters or something like that. Velocity has a unit of like meters per second, so it's a distance unit divided by a time unit because it is a rate. Okay, so we talked about the equation dirt, so okay, there you go. T is time, so this is typically in seconds or minutes, hours, etc. And acceleration, the units of that is distance units per square time units. So it's a little interesting why it's square time units, and when you get to calculus you'll actually understand all that. And I'm going to say, yay, calculus. The equation that you're going to see in Hawks is similar. It does the same sort of thing, but they've simplified it just because of their assumptions. They call this H is equal to V0t minus 1/2 gt squared. And so the reason they do this, so their H is actually D minus D0, like they move it over, that sort of thing. So just know that you can use this equation for this equation in Hawks, or this one, you'll get the same exact answers. So just be aware of the difference here. And the reason you're using this equation is because this is what you're going to see in physics if and when you take physics, or I'll say when you take physics. The acceleration that we're going to use in this equation, okay, the A and the T, is the acceleration due to gravity, okay, and that's where the G comes in here. So you notice a change from A to G, okay, fine, and it's going to be 9.8 meters per second. If you want to use 9.81, if you're familiar with that, that's fine. These are in meters per second squared units, and if we're in imperial conditions, using the imperial system, 32. Okay. The only thing that I will also say is that in our scenarios, we're going to have to keep in mind the direction. So typically, when you see if you're using this formula, as we will in a moment, we're going to attach a negative sign to these. The formula that Hawks uses, if you go through practice and learn there, already has the negative incorporated, so don't change it there. But typically when I do this, I just have to think, oh yeah, gravity is going in a negative direction, it's falling down. Down is negative as we've defined it in each of these contexts. So here, just a little quick question. Johnny launched a rocket and its maximum height is, and so it shoots up and it reaches a maximum height of 160 meters. So I just need to do a little diagram. So here's the little rocket. Okay, I'm just going to attach a little thing on the end, and then it shoots up. Yep. And then now it's going to start falling down. And it's currently at 160 meters high. Okay, and then it begins falling, and we want to know how far above the ground is the rocket 3 seconds after it begins falling. So what do I know? Okay, I know that it is 160 meters. I know there's 3 seconds. Okay, that I can clearly identify as time, and I know that acceleration is, again, it's going to be, let's see, meters seconds, so I have to use the 9.8 number because I'm in meters per second, or meters and seconds, okay? And I'm also going to attach a negative because I'm falling, okay? Now this 160, in terms of the numbers here, this is going to be where we start, right? We start, so I'm going to label that as D0. Okay, so then I'm just going to I'm going to start using the information that using the equation and the information I'm given. So D is equal to D0 plus V0 T plus 1/2 A T square. Okay, how far above the ground? Well, I want to know this distance, right? The final distance. Okay, 160. Oh, I get to V0. Do I know what V0 is? And I want you to take a moment and think to yourself, what is the value of V0? The correct answer is that V0 is indeed 0. So this language of stops means that initially, when I'm thinking of the rocket at its maximum height, it stops, so the velocity is 0. Okay, so that makes my life a little easier. So 0 times 3 and then plus 1/2, and A is negative 9.8, and then times 3 squared. Okay, so this is, now I have to get out a calculator, so I would do 160, and this is all, that's 0, and then I have to do this math. And so punch this in a calculator, double check my work. I ended up getting 115.9 meters. Okay, so I'm just going to, again, this is a context, so I need to respond with a sentence. The rocket is 115.9 meters above the ground. Okay, so this one utilized our equation that we mentioned. The only thing that really changed was that I had to figure out what V0 was, and that came from this language of stops. So in these physics problems, sometimes you might have to do very careful examination of the words to help you determine more information that's going to help you out. Okay, so that's going to be the end of this video. We'll have one more video that goes through another example of this gravity equation.